So it's the plan for the day. I was thinking, of course, if you have questions, you're welcome to. I was thinking we'd talk a little bit about some radioactive decay, exponential growth kind of stuff. Just a little. And there's a couple homework problems that are due on not today, but Friday, I think, that cover those kinds of things. And then I'm thinking we should get started on talking about antiderivatives, because that is certainly where you are going in the very near future. Well, let's do a little bit of exponential growth and decay. So here's a couple examples. We'll do one, we'll do one kind of like that. But let's actually talk about if this stuff kind of means. So let's say we have the following. Sure. Exponential growth slash decay. So in 1960, the world population. Welcome. Oh, I should give you all the attendance form on Zoom there. Just one sec. Let me. That's why I don't come on the keyboard. 1 second. Okay, go. Sure. There you go. For all those on Zoom, please fill out the attendance form when you have a moment. There you go. Cool. If someone else asks for it, someone else can share it. All right. So 1960, the world population was approximately 3 billion people. And in 2000, the world population was approximately 6 billion people. So assuming, and again, this is a big assumption, but assuming that the world population grows exponentially, which may or may not actually be true. When will we reach 9 billion people? And I want to tell you, at least according to what we're doing here, it's not going to be the year 2040, because this is not a linear growth relationship. Right? If this was a linear relationship, you could say, oh, every 40 years, the population is growing by 3 billion. So in 2040, we'd have another 3 billion. In 2080, we'd have another 3 billion and so on. But that's not what the case is. So in a linear relationship, every certain change in X results in the same change in Y. Whereas in an exponential growth or decay relationship, it's the doubling time or the half-life, the constant. So in this sort of picture here, in fact, in this example, it's relatively easy to see how many years does it take for the population to double? 40 years. So in this situation, the doubling time is what is always the same. And the doubling time is equal to 40 years. So even though it's not what the question is asking, I'm just going to tell you that according to an exponential growth model here, we would expect the population to be 12 billion in the year 2040, because that's how these sort of models work. The doubling time is always the same. So if we're assuming exponential growth, every 40 years, the population is going to double. Again, that might not actually be really true, but that's what we're assuming is true for this sort of problem. Okay, so we want to know when it's going to be 9 billion. So here's what we're going to do. We're going to say that 1960 is time equal to 0. The year 2000 is time equal to 40. And I like to make a little table with time versus, in this case, population. Say, okay, well, time 0, population is 3 billion. Time 40, population is 6 billion. And I want to know what time is it, or how many years is it going to take to get to a population of 9 billion. So this is the general kind of idea. This is how most exponential growth decay problems work. You're given 2 data points typically, and then you're asked to find out something about some third data point. Either what's the input that gets you a certain output, or what's the output that gets you a certain input. In this case, we're asked what's the input that gets us this specific output. All right, so here's how it's always going to work. Our model for exponential growth or decay is y equal to ce to the ket. Or you might use PE to the RT or AE to the X, right? You can use literally any letters you want. This is pretty standard though. What do I want to say about this? And then we're going to solve for the constants C and K. C is really easy to solve for if you have one of your data points being when time is 0 or the input is 0. And that's the case here. So we're going to start with this one. Let's use a different color here. Oh, gosh, I can do that. So starting with this data point here, we're just going to plug that in and get, well, let's see. The population is the Y value. The time is the T value. And I'm not going to write 3 billion because that's a lot to write. I'm just going to write 3B. So at time 0, my population is 3 billion, and that's equal to CE to the K times 0. The K times 0 is 0, and E to the 0 is 1. So really what we have is C is equal to 3 billion. So that constant term that's in front there, that is also typically called your initial value or your initial population, or essentially whatever amount of stuff you're starting with at time 0. That's always what you're going to get if you plug in 0 for your T or your X or whatever your input is. Of course, never enough room. I never leave myself enough room to write these things. So then after you find C, well, I should say typically after you first find C, then you find K. In some instances, you will have to find K first and C second, like in problem 2 on section 4.6 of your homework. That problem, you're going to have to find K first and C second. We'll talk about how to do it though. So for this one here, I'm now going to find K. So our model, we're going to refine our model. Our model, instead of being Y equal to C to the KT, we're going to plug in what we know C is. So we're going to say our model now is Y equal to 3 billion times E to the KT. And then we're going to plug in our other data point. So if we plug that in, we're going to get, well, our Y value is 6 billion. And we're going to get that equal to 3B times 3 billion, I should say, times E to the K times 40. And then we're going to solve that. So whenever you're trying to solve something exponential like this, you want to get the E to the stuff by itself, meaning you typically have to divide by that coefficient there. So we're going to have 6 billion divided by 3 billion, which is just 2, equal to E to the 10K. And then to get that stuff out of the exponent, we take the natural log of both sides. So I'm going to say that the natural log of 2 equals the natural log of E to the 10K. And I would encourage you to use these words when you think about what you're doing on the right-hand side. The natural log of some stuff and E to the some stuff, they undo each other. A lot of people like to say they cancel out, and while that's not technically the wrong way to do it, really they are undoing what the other one does. E to the 10K does something, and then the natural log of that undoes it. So this whole side here is just 10K. Or you could also bring down the 10K as a power and then say 10K times the natural log of E is 10K times 1. Yeah. Where did I get the 10? Did I make a mistake? I did. My 40 turned into a 10 somehow. Sorry. That's not a 10. That's a 40. Apologies. Sorry about that. I don't know how that happened. But then we can fix it really easily. Okay. 40K, not 10K. Thank you. Yes. If you ever see a mistake, let me just be like, James. Especially if I keep like, if I like, because I definitely saw your hand. I thought you had like a question. But if you're like, if I see you and I don't call on you and you're like, he's just making an error, just shout it out. Be like, hey, you're making an error. Totally cool. So then we have 40K equals the natural log of 2. So K equals the natural log of 2 divided by 40. And really you should leave that as is, meaning you don't want to get a decimal approximation. There's no real simplifying of that. It just is what it is. So then we go back and we write our final model. Our model, which is just Y equal to C to the KT with the values of C and K plugged in. So our model is going to be Y equal to C, which is still 3 billion, times E to the natural log of 2 over 40 times T. A few notation things, just so you're all aware. I think on this homework assignment, on someone, maybe it was a different class. I don't know. If you ever see so some people might write this as y equal to 3 billion, or you might see this in your web work at some point. And then you might see the letters EXP bracket, all that stuff. That means the same thing. EXP is just kind of lazy notation for e to the power of. So if you ever see EXP, it just means e to the power of whatever's in the brackets after it. All right. So now we've got our model. Now we have to answer the question that was asked, which is, how long does it take until the population gets to 9 billion? So then we're going to set, what are we going to set equal to 9 billion? Y or T? Why? Because Y is the population, right? The thing that the population is what we should be setting equal to 9 billion. On the other hand, if they asked us what's the population going to be in the year like 2030, then we would set time equal to 70, because that is 70 years after the year we started. But we're going to set Y equal to 9 billion. So we get 9 billion equal to 3 billion times e to the natural log of 2 over 40 times t. And then we're going to solve for t. And solving for t is going to be very similar to solving for k in the previous part of this problem. So divide both sides by 3 billion. And get 3 equal to e to the stuff. So we have 3 equal to e to the natural log of 2 over 40 times t. And then take the natural log of both sides. So we have the natural log of 3 equal to. So I don't really want to write the natural log of e to the natural log of 2 over 40 times t. And it's really kind of worth your while to recognize that if you ever taking the natural log of e to some stuff, you're just getting that stuff. So the natural log of this side here is going to be the natural log of 2 over 40 times t. And then you could divide both sides by this gross thing here, natural log of 2 over 40. I would instead recommend multiplying by its reciprocal. So I would say I'm going to get 40 times natural log of 3 all over natural log of 2. Right? I multiply by the reciprocal there is equal to t. Which is not a very informative answer, right? I'm like, I don't know how many years 40 natural log of 3 over natural log of 2. So this is a time where you should actually get a decimal approximation. So you should throw this in a calculator, and when you throw it into a calculator, you get approximately 63 years. Now I should point out, technically that's not the answer to the question. They didn't ask how many years is it going to take from when we had a population of 3 billion to get to a population of 9 billion. They said, what year is it going to be? So I need to take my t equals 63 years and say, oh, well, I really started in 1960. So 1960 plus 63 years is going to be the year 2023. Which I don't think we're going to get there, right? I hope we're not going to get to 9 billion people in 2 years. That would be probably problematic. So that is the year that this model would predict that we would reach a population of 9 billion people. Again, it's all dependent on how accurate your model is. And usually people growth on a large scale is not very accurately predicted by exponential growth. There are better models for people growth because, right, there's limited resources and all that kind of stuff. It's more of a 17 series kind of situation. Like in the 17 series, they talk a lot more about like populations and logistic growth and like animals, predator, prey, that kind of thing. Not so much in this one, which is fine. So let's go ahead and let's do an example like problem 2 from the homework, because I definitely, in office hours earlier today, I definitely saw a lot of people struggling with that question. So let's look at number 2, and I'm just going to make up some numbers here. So this function, y equals c e to the kt, passes through a couple points. And I should really mention, this is the same information, this is the same kind of problem we just did with one slight variation. I'm just giving you 2 data points. In the previous problem, they were associated with information, right? Like time and population. In this problem, they're not. We're just giving you x, y coordinates. So this graph passes through the points. And do I want to make it hard or not hard? I want to make it not that hard. Let's make it not too terrible. Let's say that the points 1, 6 and 5, 13. I kind of made that easier. It's all right. It'll be fine. 1's a little easy, but it's okay. So our job is to find what I would really say is if I were asking you this, I would say find the model, which really just means find C and K. So if someone says find the model, you already have the model. It's y equals c to the kt. They're just asking you to fill in the constants c and k. So find the model, aka find the constants c and k. And here's what I want to say about that. If you're given a point where the input value is 0, finding c is a straight shot. Like if this was 0, 6, I would know that c was 6 right off the bat. But it's not. It's 1, 6. And so what we have to do instead is work a little harder. And actually, we're going to find k before we find c, which always feels wrong to me, but it's what we're going to do. And that's not much wrong. It's just atypical. So I'm going to plug in both points. I'm going to say, okay, t is 1, y is 6. I'm going to get 6 equal to c e to the k times 1, which is just k. And the other one, I'm plugging in 13 for y and 5 for t. So y, oops. Ooh, 13, come on, all right. 13 equals c e to the k times 5. And there's a couple ways people like to do it. There's literally a couple ways people like to do this. One way, which I always find kind of weird, but it's actually pretty slick. One way is to divide these equations. Divide them. Meaning literally take probably the one with the higher power, take this equation and divide it by that equation, which always seems weird to me, but it's totally true. If two numbers are equal and you divide them by two numbers that are equal, they're still equal, right? 5 equals 5, 2 equals 2, 5 divided by 2 equals 5 divided by 2. So if things are equal, you can divide them by other things that are equal. It feels a little strange, but it is totally correct to say that I'm going to take this one, 13 equal to c e to the 5k. If I divide by 6 equals c e to the k, that's a true statement, which is kind of neat. We especially know we're not in any danger of making a colossal mistake here because we're not dividing by 0 on either side. E to the something can never equal 0, so there's no worries about dividing by 0. Yeah.
So would this just be called like a system of equations thing?
Yeah, but I would say that typically in systems of equations, we often don't divide an equation by another equation, although it is a valid operation. It is not something we usually do. So that's one way of getting here. And then if you check this out, 13/6 equals, cancel the c's, and e to the 5k divided by e to the k, subtract those powers, and you get e to the 4k. And then solving for k is relatively easy. I'm not going to finish it though yet because I want to show you the other way you could do this. So you could do this. You could solve each equation for c. So this first equation, if I divide both sides by e to the k, I get c equal to 6 divided by e to the k. And in the second equation, if I divide both sides by e to the 5k, I get c equal to 13 divided by e to the 5k. And then I can set those two c's equal to each other. So I can say 13 over e to the 5k equals 6 over e to the k. And then I can divide both sides by 6. And I can multiply both sides by e to the 5k. And get to exactly right there. So you're really going to get to the same place either way you do it. It just depends on how you want to see it. This one here. So I suppose I meant I showed all my work, which is fine. So what I did from here was I took 6 equal to c e to the k and divided both sides by e to the k. Let me zoom in. I can't zoom in forever. I can. It's hard to make sure that things are kosher for everybody. So we can see that a little bit better. And then for this one, I did the same thing. I took this and I divided both sides by e to the 5k. So I have 13 divided by e to the 5k. Oh, thank you. That's what happens when you zoom in. Equals c e to the 5k divided by e to the 5k. And here, the e to the 5k's cancel. Here, the e to the k's cancel. That's how we're getting there. Either way you do it, eventually you're going to get to e to the 4k equals 13/6. which will, let me zoom back out. Which will then, if we take the natural log of both sides, natural log of 13/6 equals 4k. So k equals 1/4 times the natural log of 13/6. So there's your k. It's not pretty, but it's fine. Now, the thing about doing it this first way, so I guess I'll make a little dividing line here. The thing about doing it this way is if you do it this way, you don't actually have c isolated. So if you want to go back and find c, you're going to have to plug in k to one of these equations and then solve for c. On the other side, if you do it over here, you kind of have already done the work of isolating c. So if you want to find c, you can say, well, I'm going to use this equation here. So if I use that equation, I can say, well, c is going to equal, it's not going to be nice, 6 over e to the k, 1/4 natural log of 13/6. Kind of gross. You can make it slightly nicer to plug into web work, but not a lot. I will show you though, because I think it's worthwhile. So one thing you can do here, which people sometimes will do with solutions, is if you have e to a number times a natural log of a number, this 1/4 can come up as the power on 13/6 in the natural log. So I can rewrite that as 6 over e to the natural log of 13/6 to the 1/4 power. Where I should say it's natural log of all of that. Natural log of 13/6 to the 1/4 power. And then we have e to the natural log of a thing. And e to the natural log of a thing is just the thing. So you could totally rewrite this, although it's not much better, as 6 over 13/6 to the 1/4 power. Still not particularly lovely. You could even make it slightly simpler, but I think that's good enough. You can make it slightly simpler by saying you have 6 to the 1/4 times 6 on top. So really you have, I can't help myself, sorry. You have 6 to the 5/4 over 13 to the 1/4. Still terribly ugly, but whatever. So that's how that kind of problem works out. And I think that's kind of the only way you can really do it. I should say one of those two ways is the only way you can really do it. You have options. All right, let me ask before we move on to the next chapter. Are there any questions about really anything from chapter 4? Really anything? Like, are there any homework questions you want me to do one like? Are there any other topics from chapter 4 we should revisit before we move on to talking about antiderivatives in chapter 5? For the Zoom people too. Zoom folks, is there anything you want to see covered before we move on to the next section? Yeah.
The derivative of y equals x over x.
Let me try that. So let's see. So we want to find the derivative of what?
Y equals ln x
Over x to the third? Sure. I'm going to change it up a little bit. I'll make it x to the 7th. Okay. So if we have to find the derivative of something like that, what rule do we need to use? Quotient rule for sure. So we could even kind of give ourselves a little bit of room to work here. So if I want to find the derivative, which you can write as dy dx, I'm just thinking of it as the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. And then we should simplify this. So let's see. So I'm going to have x to the 7th times the derivative of the natural log of x is 1 over x. And then the derivative of x to the 7th is 7x to the 6th. Be careful when you're writing something after the natural log of x there, that 7x to the 6th is not in the natural log function. So it might be in your interest to write like parentheses around the x there to make sure you know you're just taking the natural log of x. I would probably rewrite this with the 7x to the 6th in front of the natural log of x, but you don't have to. All over x to the 14th power. And then if you're putting this in web work, you totally could leave it as is. if I was putting this in web work, I would want to make it a little bit, I don't want to type x to the 7 times 1 over x. I can simplify that relatively easily. It's going to be easier to type in if I do this simplification. So I'm going to write that as x to the 6th minus 7x to the 6th times the natural log of x all over x to the 14th. And really, I see some other simplifications we can do. We could factor out an x to the 6th from the top. We're left with a 1 minus 7 natural log of x all over x to the 14th. And then we can cancel an x to the 6th here and an x to the 6th there. So really, this simplifies actually pretty nicely to 1 minus 7 natural log of x over x to the 8th power.
Where did the 1 over x go?
So where did the 1 over x go? What is x to the 7th times 1 over x?
Oh, x to the 6th.
Right, exactly, right there. So you definitely don't have to simplify this all this way, but I will say sometimes it's worth the effort to simplify it because typing, there are some really heinous things you sometimes have to type into web work. And sometimes they can be made a bit less terrible by actually doing some of the work on paper before having to type it in. Because like sometimes things really just do get very messy. Let's see, anything from the folks on the room? Take a look here. Nope. Other stuff. Is there anything else I thought was terrible? Yeah.
Is there any way to do like a gross second derivative?
Sure. Yeah. Let's see. Let's take a look here. Yeah, let me look for some inspiration. I'm gonna not, because I don't think you have to do one like that. Yeah. I was gonna say I don't want to do an exponential one like that though. Sure. Yeah, let's make it real terrible. Okay. So let me keep my notes in order here. What if we had to take the derivative of something like, I don't know, let's make it awful. Let's say f of x equal to, sure. Let's say we had, okay, how gross do we want to get? Okay, let's say 6 to the x squared times log base 2 of x plus 3. Ooh, that's gonna be gross. We're gonna take the second derivative of that? Oh, I don't know. All right. Okay, so I see right off the bat a product rule. I've got one piece here, 6 to the x squared, times another piece here, log base 2 of x plus 3. So at the very kind of top level, I'm thinking it's going to be u prime v plus uv prime. Okay, so we're going to get, yeah, I'm not even going to write that down. So if I start taking the derivative, what's the derivative of 6 to the x squared? There is a rule for it, right? You could use logarithmic differentiation to find that derivative, but you don't have to. So I remind everybody, when your base isn't e, what do you know we're going to multiply by at the end of that?
Natural log of
Right, the natural log of our base, natural log of 6. I guess technically that's always true, right? Even if the base is e. So whenever you have an exponential thing, you're always going to multiply by the natural log of the base. It's just that if your base is e, natural log of e is 1. So the derivative of 6 to the stuff is 6 to the stuff times the derivative of the stuff, and then we do need a natural log of 6. So there's our u prime. And then we leave v alone. Times log base 2 of x plus 3. Should have made that log more complicated. Oh well. And then we switch it around. We leave the first thing alone, 6 to the x squared, and we multiply by the derivative of the second thing. So just like here, when our base was an e, we multiply by the natural log of our base. For a logarithm whose base isn't e, you're going to end up also dividing by the natural log of that base. So here, our v prime is going to be, well, the derivative log of some stuff is 1 over the stuff times the derivative of the stuff, which happens to be 1 here, so it's not so bad. And then we also have division by the natural log of 2. I usually write it at the end as 1 over natural log of 2, but you could totally write it as one fraction, 1 over parentheses x plus 3 natural log of 2 if you wanted to. Now, here's my advice in general for finding second derivatives. It is worth your while to simplify the first derivative before finding the second derivative. Or really, that's actually just my advice in general for finding derivatives. It is worth simplifying the function you are looking at
before you differentiate it. So if there's some meaningful, worthwhile simplification you can do, it's usually a good idea to do it.
So to that end, is there any simplifying I can do here? I see I can factor out a 6x squared from both pieces. That seems probably worthwhile. So I'm going to factor out a 6 to the x squared, not a 6x squared. So I'm factoring that out and I'm left with, let's see. I'm going to have a 2x times natural log of 6 times log base 2 of x plus 3. Okay. Plus, I'm going to write this as one fraction, 1 over x plus 3. Yeah, times natural log of 2. All right. Now to take the second derivative. Okay. So we still have two pieces. I will certainly admit this second piece is much worse than the first piece, but still at this level, we have to be like, okay, I have one piece times another piece. So the derivative of 6 to the x squared, we already did it. And that's a nice thing about repeated derivatives, especially if you have something exponential. Usually you've already taken the derivative of that exponential part in the first part. So you don't have to like do the mental work again. Just be like, oh, well, when I took the derivative of 6 to the x squared, I got that. I'm taking the derivative of 6 to the x squared, I should get that again. So it's going to be 6 to the x squared times 2x times the natural log of 6 times all of that garbage. 2x times natural log of 6 times log base 2 of x plus 3 plus 1 over x plus 3 times the natural log of 2 in the denominator. Plus, now we do it the other way. Okay, so we're going to leave the first part alone. That seems relatively not terrible. And then the derivative of the stuff in the brackets is going to be where we're going to have to be extra careful here. So looking at what's in the brackets, I see a product rule. So I'm thinking of this as one piece because that natural log of 6 is just a constant. So the derivative of 2x natural log of 6 should just be 2 natural log of 6. That's it. Because what's the derivative of x? Right. What's the derivative of a constant times x? The constant, which is 2 times natural log of 6. And then we're going to leave the other piece alone. I guess I could give letters here. I could use G and H. So this is G prime. And now we're going to have H. It's going to be log base 2 of x plus 3. And then we switch it up. Then we leave G alone. So we get 2x natural log of 6. G. And we multiply by the derivative of log base 2 of x plus 3, which I will also point out we've already done in the previous derivative. So right here, the derivative of log base 2 of x plus 3 is that stuff right there. 1 over x plus 3 natural log of 2. Well, that makes it convenient. Okay, but then we also have to take the derivative of this piece here. Okay, here's what I would encourage. So I don't want to use the quotient rule. And the reason I don't really want to use the quotient rule is because the numerator is just a constant. So it's not very interesting. I would encourage you to think of this piece. I feel like I say that a lot. I would encourage you to do this. I'm very encouraging in class. I would encourage you to do a lot of things. I would encourage you to think of this as the constant 1 over natural log of 2 times x plus 3 to the negative first power. That's what I would encourage you to think of it as. Because to me, that's the easiest way to take its derivative. That 1 over natural log of 2 constant multiple is just going to hang out. The derivative of some stuff to a power, well, the power comes down, and you have your stuff to the 1 less power, and minus 1 is minus 2. And then you would multiply by the derivative of the inside stuff because of the chain rule, but the derivative of the inside stuff is just 1. So we're not going to write that down. There's a heinous second derivative for you. I might have made it a little more complicated than really necessary, but that's the gist. So I would say when you're doing second derivatives,
one, simplify your first derivative if there's any meaningful simplification to do, and two, look for work you've already done. Right? If you're taking the same derivative again, look back at your first derivative, like, oh, well, I already know what it's going to be. It's right there. Good question. Other questions about chapter 4 stuff? Yeah. Like finding the slope and then finding the equation of the tangent line? Sure. Is there a problem on the homework it's similar to? Can you tell me which one? Sure. Yeah. So actually, I'm going to go back to, I feel like this might have been what that other question was also kind of referring to. I'm going to go back to this problem we did previously, because I feel like that's what that problem was actually getting at. So what I want to do is, here's the question I actually want to ask. So for this question, let's go back in time to 5 minutes ago. What I really want to do here is I want to find the slope of this function, y equals natural log of x divided by x to the 7th at, now I'm always kind of jealous because like these web work problems give you both the x and y coordinates. I would never be that nice. I'd be like, I'm going to give you x equal to e. So I would say at x equal to e, but they're nice. They plug in e for you to the function, and they say at e comma. If we plug in e, what do we get? What's the natural log of e? Everyone, show me on your fingers, or you can say it on. It's okay. I was slow on the draw there. I should say, show me on your fingers and then tell you what I want you to show me. Natural log of e is 1, and e to the 7th is just e to the 7th. You're kind of stuck with a gross e to the 7th. So if I want to find the slope of the line at that point, I should really say to find the slope of, I don't like the way they've written this personally. I would say find the slope of the line tangent to the graph at that point, because that is, I mean, technically, sure, it's the slope of the graph at that point, but the more normal way of expressing that is the slope of the tangent line to that point. Oh, well. So if I want to find the slope of this line, I'm just going to plug in my x value to my derivative. So I would say that the slope of this line is dy dx evaluated at x equal to e. Or if you've called your function f of x, and this is f prime of x, you could say that we're finding f prime of e. So all we're really going to do, and so this is exactly why you want to simplify your derivative. Because plugging in e here, although not super terrible, is not going to look nice. E to the 7th times 1 over e minus natural log of e, which is 1 times 7 e to the 6th over e to the 14th. I don't want to simplify all that. I want to have done the simplification first, so that when I plug it in here, it's not too terrible. So if I find dy dx evaluated at x equal to e and plug it into the nice finished product I've got over here, it's going to be 1 minus 7 times the natural log of e over e to the 8th, which natural log of e is just 1. So 1 minus 7 over e to the 8th, which is negative 6 over e to the 8th. And then often, I've got this little thing clicked on over here. Apologies. For those of you on Zoom, if you ever see, like, I assume you can see like the little camera thing that I just clicked off of the visualizer. If that's ever up there, just let me know. I will click on it because it makes it harder to see what's on the page. So let me know if that's a problem. Typically, and it is in this problem, typically the follow-up question to find the slope of the tangent line is to find the equation of the tangent line. So if I'm finding the equation of the tangent line, I am always personally going to go to the slope point, the point slope form. I'm going to do y minus the y coordinate equal to the slope times x minus the x coordinate. That's your point slope. Y minus y1 equals your slope times x minus x1. But the problem here is they don't want you to write the answer that way. You can't. They've given you this prompt that says write it as y equals something. So the easy, not doing any work kind of way, or not doing much work kind of way, is just to add 1 over e to the 7th to both sides. So you say, okay, y is going to equal 1 over e to the 7th minus 6 over e to the 8th times x minus e. And you can totally get away with that here. Now, a way that sometimes web work tries to get around you not simplifying this is asking you, what's the y-intercept? Because you can't see it when it's written like that. You actually have to do the work of multiplying it up. So if we were to be a little bit more, I don't know what the word I'm looking for is, if I was to ask you what the y-intercept was, we'd actually kind of need to write this out and figure out a whole piece of paper for this one part, James. You can't find it? No, fine, okay. So if we wanted to actually write it in slope intercept form, we would distribute the 6 over e to the 8th, and we would have y equal to 1 over e to the 7th minus 6 over e to the 8th x plus 6 over e to the 8th times e. But 6 over e to the 8th times e, one of those e's is going to cancel. That's going to be a 7, and that's going to cancel. So really, here's what you've got. You've got y equal to 6 over e to the 7th. I'm going to write first, plus, I should have wrote last. What a terrible thing to do, James. Minus 6 over e to the 8th x. And then I can add those together because they already have a common denominator. So I can write y equals, I should have written this first because that's like the standard way of writing. Sorry. So y equals mx plus 6 over e to the 7th plus 1 over e to the 7th is 7 over e to the 7th. So this is totally the what you can get away with in web work answer. And this is the what people would really want you to write answer. But yeah, unless someone says to actually do that, it's not really good, right? They're both the same equation of the same line. Cool. It's a good question. All right. Other things from chat. What time is it? What time do we end? 3 o'clock. Okay. I get to on Tuesday, Thursday, my classes are 2 hours and an hour and a half. So I'm always kind of in that mindset before I'm here on Wednesday. I'm like, oh wait, this is just an hour. So I need to like. Okay, so unless there's any burning questions from chapter 4, I feel like I should set you up for at least a little bit of talking about antiderivatives. And so here's what I would like to say first about antiderivatives. If you know how to take a derivative, in some sense, you know how to take an antiderivative. The antiderivative, it's similar, but not exactly the same to how inverse functions work, kind of. Except it's an inverse operation, meaning you're looking for the thing that undoes what another thing does. So for example, f of x equal to x to the 3rd. This is a very straightforward example. And g of x equal to the cube root of x are inverse functions. They undo what the other one does. For example, f of 4 is 4 cubed, which is 64. On the other hand, g of x completely undoes that. If you plug in 64 to g of x, g of 64 is the cube root of 64, which is of course 4. So I really, really want you to understand that antiderivatives take an input. So instead of having a number that's an input, like so for these inverse functions, your input's a number, your output's another number. And one function does one thing, takes one input, gives you one output. The other function takes that output, puts it back in the input, and gives you back the original thing. For derivatives and antiderivatives, your inputs are the functions. So I'm going to say, so like for a derivative, right? My input, for example, my input is going to be f of x equal to x to the 4th. And I'm going to say the derivative of f of x is equal to the derivative of x to the 4th, which is 4x cubed. Now I'm going to take that output and undo what I did with an antiderivative. So the antiderivative of 4x cubed should get me back to where I started with a little bit of a thing we have to talk about, but mostly that. So if I'm going to anti-differentiate 4x cubed, literally when you read the antiderivative, you should ask yourself, what function can I take the derivative of to get what's in there? Well, it's on the page. What function can we take the derivative of to get 4x cubed? It's x to the 4th. Yeah, we'll talk about it. We're about to talk about that. So, right, I really want to emphasize though, right? If you took the derivative of x to the fourth, you get 4x cubed. You take the antiderivative of 4x cubed with respect to x, you get x to the fourth. And then, yeah, it could be plus 5. Because what's the derivative of 5? It could be plus 7, because what's the derivative of 7? So it could be plus any constant. So technically, these don't quite exactly undo each other, but it's close enough to talk about it that way. Typically, when you're finding the general, indefinite integral, aka the antiderivative, and we'll talk about integrals, antiderivatives. There's a whole lot of language to talk about in a minute or next time. When you're finding the antiderivative, it's the general antiderivative, so you just tack on a plus c, because you could always have plus a constant, and the derivative of that constant would be 0. Okay, so derivatives get you somewhere, antiderivatives undo where you were and get you back to where you started. And there are a lot of very general rules about antiderivatives. Oh, I know what I want to say first of all, though. This notation, so what do I want to say in 5 minutes? What do I want to say? Okay, so here's what I would say. When you read this, when you read the derivative of x to the fourth, you take the derivative and you don't write that anymore, right? You don't write the ddx or the prime or the whatever notation you use to mean taking the derivative, because that's an instruction. It's telling us to do a thing. And then we did the thing, so we don't need to write the instructions anymore. The same thing is true down here. What I would really like you all to take away from this is these symbols right here are just instructions. And those instructions are telling you to take the antiderivative. I should really say this big S looking thing is telling you to take the antiderivative, and this dx over here is telling you what variable you are anti-differentiating with respect to. Just like in the derivative here, this dx on the bottom is telling you what variable you are differentiating with respect to. Okay, so in general, for antiderivatives, there's a couple nice rules. Well, actually, I should say, if you know how to take the derivative of something and get an answer, you know what the antiderivative of that answer is. So there are lots of functions you know how to differentiate, like what's the derivative of the natural log of x? Right. So you know that the antiderivative of 1 over x is the natural log of x, with a caveat we'll talk about later. There's a caveat that we have to talk about later. Or, for example, if you know that the derivative of sine of x is cosine of x, you know that the antiderivative of cosine of x is sine of x. So there's this very back and forth relationship that that's like the heart of all of this. If you can get that idea down, that you're just undoing what a derivative does, you're going to be fine. But then there's some other functions that are harder to differentiate. We're not there yet. We will be there soonish. What's the difference between, so the difference between antiderivatives and integrals is that an antiderivative is specifically for a function, and we associate that with what's called the indefinite integral. Whereas we will also talk about definite integrals, which are associated with the area under the curve of under the function. So there's this very natural relationship between what an antiderivative is and an integral is. And people do use them very interchangeably. You will hear me say antiderivative, you'll hear me say integral mean the same thing. I'll try to be specific about how they are slightly different, but really, as far as we're concerned, you could think of an indefinite integral, meaning you're not trying to find the area under a curve, as the same thing as the antiderivative. But it can be a little nitpicky. So just for example, if I wanted to find the antiderivative of x to the sixth, I'm looking for the function that if I took the derivative of it, I would get x to the sixth. And I know that when I take the derivative of a function, the power becomes 1 less. So I'm taking the antiderivative, the power needs to be 1 more. But the answer is not going to be just x to the 7th, because what's the derivative of x to the 7th? Right, and I'm off by a factor of 7. I should say I'm off by a multiple of 7, because constant multiples can be easily adjusted for. If I want to adjust for a multiple of 7, I'm just going to multiply by 1/7 or divide by 7, whichever way you want to write it. So we could say this is equal to 1/7 times x to the 7th plus c, or if you prefer, x to the 7th over 7 plus c. Because if you take the derivative of x to the 7th, you get 7x to the 6th, and then times that by 1/7, you get x to the 6th. So this is exactly because the derivative of 1/7 times x to the 7th plus c
is equal to 1/7 times 7x to the sixth plus 0, which is just equal to x to the sixth.
You don't typically ever have to check that your antiderivative is correct by taking its derivative again, but if you wanted to, you should be able to. That's something that is one way to check. The problem is, I'll say usually if you're making a mistake taking the antiderivative, you're probably making a similar mistake getting back to the place you started with. So it's usually not a very good check because if you're making errors one way, it's usually not going to fix the errors the other way. But it's still a check. So the last thing I'll leave you with for today is the general anti-power rule. So we know, first of all, the derivative of x to a power is that power times x to the 1 less power. And the antiderivative of x to the power is x to that power plus 1 divided by the new power plus 1, plus a constant. With one exception, of course, that power can't be -1. Because if it was, you'd be dividing by -1 plus 1. We already know the antiderivative of x to the negative first, aka the antiderivative of 1 over x. It's the natural log of x. So this is definitely, at least in the beginning here, there's your bread and butter antiderivative rule. You're going to use that a lot. You want to get real comfortable to be like, oh yeah, antiderivative of x to the third is x to the fourth over 4. Antiderivative of x to the 2/5 is x to the 7/5 divided by 2/5, or x to the 7/5 times 5/2. So try to get some practice in being comfortable with just anti-differentiating x to any power. Could be positive powers, could be negative powers, except for -1, could be fractional powers. I would especially practice some fractional powers because they do come up. All right, it's 3 o'clock. I should stop.